Oh, I didn't see you there. Just failing at falling up. Falling? I wonder how strong gravity is in Geometry Dash. Hello, Count Sacke here, back with another GD Dynamics video. Today we're going to talk about gravity. This is important to know because we actually need to calculate a value for gravitational acceleration to be able to apply projectile motion to Geometry Dash, and well, there might be some other things that might come along the way. I should mention that if you have not watched episodes 3 and 4 yet, do so, otherwise things might not make sense. To get things started, let's define gravity. Gravity is the curvature of four-dimensional space-time, and this is the Einstein field equations, which is a set of partial differential equations. What are you talking about? What? Oh. Okay, sorry. Let me be clear. I'm actually correct as of the current definition of gravity. However, I highly doubt that Robtop coded space-time into a 2D platformer. Basically, general relativity is way too powerful for what we're going to do. As much as I would like to talk about the geometry of spacetime in GD, future episode, I'll have to save that one for another time. So let's go to a simpler model, Newtonian mechanics. In Newtonian mechanics, gravity is simply an attractional force due to the masses of objects. This is Newton's law of gravity. It tells us the magnitude of the gravitational force, and its most practical use is around the scale of the planets, so this equation is still actually overkill. So let's zoom in onto the surface of, GD world? Oh, not the app, you know what I meant. On this scale, the ground looks basically flat, and objects would appear to fall straight toward the ground, exactly in the same direction of the gravitational field. A field is a sort of space wherein at any place in it you have a number, a tensor to be more precise, assigned to those points. For example, coordinates in space are actually a field, specifically a vector field with three components, the x, y, and z. So actually, it would actually be more accurate to call coordinates a position field. Meanwhile, the gravitational field is a vector field that describes how much and in what direction a gravitational force will be exerted on a mass at a given distance from another mass. Gravitational fields have their vectors pointing towards a mass, which makes sense since objects that are gravitationally attracted to each other go towards each other. The main important detail about this is that if there's a mass, a gravitational field will be present directed towards it. A gravitational field can exert gravitational forces onto any mass present in that field. There are a lot more details we could go into, but let's get back to the surface of GD world. On the surface, the gravitational field is actually pointing directly downward, though it doesn't appear to be curved or anything like that. If forces are still too powerful for what we're trying to accomplish, then what we need is kinematics. Kinematics basically describes the motion of objects. With that, we have some terms to talk about. Vector S is displacement, or the change in position, while vector V, velocity, is the change in displacement. And lastly, vector A is acceleration, which is the change in velocity. Sure, it's cool to know what they mean, but how does one affect the other? To answer that, I need calculus. Just remember these terms and it might be easier to read what the derivations mean. I would love to teach calculus, but this video ain't got the time for that. So this is a differential equation I'll be solving. However, I will only be dealing with the case where n is equal to 2 because acceleration is the second derivative of displacement, and we don't really need anything more than that. So we set n equal to 2, and that leaves us with the statement that the second derivative of displacement is equal to acceleration. So all we have to do here is we take the integral with respect to time on both sides. And that eventually results to this statement. The derivative of displacement with respect to time is equal to the final velocity, which is then equal to acceleration times time plus the initial velocity. However, we can still continue on because we still haven't solved the differential equation. We've only solved it for velocity. So what we have now is that if we take the integral with respect to time once again, we find that the final displacement is equal to the acceleration times the time squared divided by 2 plus the initial velocity times time plus the initial displacement. With that, we can finally describe the motion of objects in uniform acceleration. Delta V is equal to AT, and delta S is equal to AT squared divided by 2 plus VIT. This triangle here is delta. It basically means the change in blank, and it can be described mathematically in this way. Delta X is equal to X sub F minus X sub I. Here in Desmos, we have a change in velocity against time graph. In uniform acceleration, the velocity is linear. Now here is a change in displacement against time graph. With uniform acceleration, there are different ways that this graph could look like. If the acceleration is non-zero, the change in displacement is parabolic. While if it is zero, it becomes linear. The reason for the parabolic shape is because of this term. However, if the acceleration is zero, it cancels out and you're left with this term. But how can it move when acceleration is zero? Alright, that's a common misconception. Zero acceleration does not mean zero velocity. Remember the equation and read it out carefully. The change in velocity is acceleration times time. So an object can have no acceleration and move since the velocity is not zero. These two equations look very similar, but they have very different meanings. Now we can solve for gravity, but in order for things to make sense, we need to talk about the basics of 2D vectors and projectile motion. A 2D vector can actually be represented as the sum of two component vectors, like here on the screen. If you want to get the components, you just use trigonometry. You're most definitely familiar with the sum of scalars, but vectors are different. You do it like this. You take the first components of the vectors and add them. This will be the first component of the vector sum. Then take the second components and add them, and then so on. The geometrical representation of vector addition is to take one of the vectors and to slide it to the tip of the other vector. This gives us the same values from our computations, and if we draw another arrow from the origin to the point, we can see that we get the resultant vector from the sum. Now, let's talk about projectile motion. Projectiles are objects in freefall, meaning that the only force being exerted on it is gravity. There are three situations for projectiles taught in your basic physics class, but we only need to focus on one of them. This situation is pushing an object off a ledge. We could look at the displacement of the object, but I think it would be better to look at the velocity as it shows the conditions for this situation in projectile motion. In this case, velocity throughout the entire path is represented with this vector. The x component of the velocity vector is vi sub x, or it's basically the initial velocity given at the start when pushed off the ledge. Then the y component is given by negative gt, where g is just the gravitational acceleration. The horizontal velocity remains constant throughout the entire path. Specifically, it's the same velocity that was given to it when you pushed it. This might seem weird, but think about it. Gravity is the only force acting on it, projectile. The gravitational field is pointing directly downward, so therefore the gravitational acceleration would only act upon the vertical component of the velocity. With that established, we have to talk about how gravity works in Geometry Dash. It actually depends on your game mode, but we can nail down some things. For the cube, ship, UFO, and robot, you start falling off according to the displacement equations. However, after some time you might notice that the motion is no longer curved. And remember what that tells you? It means a constant velocity. And this constant velocity is actually called the terminal velocity. However, for the ball and spider, it seems to have no terminal velocity. Alright, let's do some algebra to get equations for the gravitational acceleration. we have delta v is equal to at, and we have delta s is equal to at squared over 2 plus the initial velocity times t. We can't really do anything with the first equation since it has too many variables that are unknown at this point in time. Speaking of time, that's exactly what we need. Taking a look at the horizontal component of the second equation, we can actually solve for time. The acceleration is just 0 meters per second squared, and the initial horizontal velocity is the player's speed. This was calculated in episode 4. From the second equation, we find that time is equal to the change in the horizontal displacement divided by the horizontal component of the initial velocity. So now we can look at the vertical component of displacement. We know we can calculate time, and we know the initial velocity is just 0 meters per second. So with that, we can solve gravity. So after some algebra, we find that the gravitational acceleration is equal to 2 times the vertical displacement divided by the time squared. We can finally calculate gravity. And well, guess what? Gravity is completely different depending on speed and game mode. Though we can rule out just one mode, the wave, since it doesn't accelerate at all due to gravity. I also checked if the mini versions had a different acceleration, but they don't, so we don't need to record values for the mini modes. Here is my methodology for calculating gravity. You set up a scene that looks something like this. The ramp here is just to account for the ship, ball, UFO, and spider since the camera is locked vertically. Then we just place a start position and select whatever mode and speed you'd like to solve for. After that, go into playtest mode and just let the path be drawn out. Next, we take a screenshot and do pixel measurements for beta. This next step is very important, so pay attention. I want to measure from the point where the player immediately begins to fall and pick any point along the curved part of the path. If you choose a part that is linear, it will make our value for gravity incorrect. Now, with that, here are the calculations for gravity, and take a look at these stunning tables. I would like to mention that I originally had a different method for calculating the gravitational acceleration. However, using these equations was actually a lot more prone to human error. So, we've managed to calculate gravity in GD, and well, like many times in the series, I don't believe anyone has done this before, and well, now you know. Be sure to look out for the second part of episode 6, which is where I calculate the terminal velocities for the cube, ball, ship, and UFO. That's really about it for now, so thanks for watching and hope you've enjoyed.